the next thing, or one of the biggest topics in the data preparation for AM is to find an orientation, as I said beforehand. And therefore we developed this orientation map, and I have selected the part, and I can now calculate those orientation maps in this case. And what are they visualizing is you can find every orientation of the part inside the build chamber, inside this map, in this current setting map. And what they are representing is based upon criteria, and then we are offering three criteria here. And the first one, which is pretty easy to understand, is build speed or build up speed or build time, however you want to call it. And the build time of a part, so the time which is necessary to build up the structure, is based upon the orientation. So a red orientation ends up in a very high orientation of the part. Green orientation indicates low build time. Why is this the case? The volume which has to be scanned, the volume of the part, is always the same. So the volume that has to be solidified is always the same. But when you have an orientation which is very high, you have to do more recoater movement. So each layer, a recoater movement has to be done. And so the build time is influenced by that. And the high orientation indicates more layers, or more layers which have to be produced in comparison to a flat orientation of the part. What I find very interesting or very helpful is that you can see this part has two red areas, and that's the reason because it's a symmetrical part. So you have to find two orientations here. Yeah. Another criterion is support. Supporting areas based upon the overhang angle, because what I have shown in the presentation beforehand, this one, the flatter the overhang is, the more scanning in the loosened powder is affected, and so you can identify a boundary angle till which overhang angle you need support structures, and at which overhang angle you do not need any support structure, because the bending is not that critical anymore. And nowadays in metal AM, the boundary angle is at about 40 to 45 degrees, round about that, depending on the material. This is a value or a parameter which is very highly depending on the material you are working with. So aluminum, for example, is not that critical. You can print down to 40 degrees. In comparison, titanium, for example, you have to support till 45 degrees or something like that. And this boundary angle can be defined in the settings of the material, so you can find them here for all materials which are in my material library. This overhang angle can be defined. Pretty simple. Okay, so support volume or supports are identified based upon this critical angle, and what you can see here, this highlighted areas here all have to be supported later on. And we can simply calculate the amount of supports per orientation. And again, we can find good orientations in context of support. So here in this orientation, I only have to support this big area, which is not pretty high, and some smaller areas here in the inner, in comparison to that orientation, which indicates a lot of supports, a lot of big supports here in the inner, and they are pretty high in comparison to the rotation, to the orientation beforehand. Well, so pretty easy. Again, you can also find red and green areas in the map, which indicates less support. And last but not least, the distortion. The distortion can be calculated based upon a finite element analyze or whatsoever, but this will take a lot of time. And our users wanted to have a quick first guess what is an orientation which will be beneficial in context of deformation. And we found a map, or we could calculate the map which indicates exactly that. And the reason for that is in a green orientation, the build-up is very homogeneous. You begin with a small area, and it's increasing pretty smooth, and it's decreasing at the end. In comparison to that, when you think about the red, or when we take the red orientation, you can find again a pretty smooth build-up, but the expansion, or the expansion in X and Y direction, or in this case in X direction, is pretty big. And when you think about the thermal expansion thing, or the shrinkage, a big expansion in one direction indicates a lot of shrinkage. And this indicates deformation, more or less. So when you find an orientation like this one, which has smaller XY expansions, it's more beneficial than to have an orientation which is has bigger XY expansions. Yeah. Again, which I have missed, is I entered the C key on the keyboard to activate and deactivate this cutting plane. You can access to this functionality also over right-clicking on the part, Tools, View Cut. You can deactivate the function simply by Escape, or by clicking or deactivating the part. Yep. So we have now spoke about these single criteria, and as a user, I can now define a weighting of those three criteria, which means by simply moving the cursor inside this triangle, I can give different weights on those three criteria. And for example, build time is not so important for me, but less support and less deformation is very important for me. Then I have to move the cursor more down to this bottom line here. If build time is also interesting, then you can move it a bit upwards, so more into the middle, for example, and then you can find a green orientation here, which is this flat orientation. Probably in this case, this is a good orientation. But depending on the weights that you as a user define, this current setting map always updates. And this gives you the possibility to find the orientation based upon your needs. Yeah.